Hello everyone, my name is Neil Jackson and this is my lab report over the fourth lab titled Oscillations. So our system consisted of a spring and a weight, and it was oscillating not only up and down but also left to right. And our job was to analyze this motion and to kind of explore it a little bit. So this may sound really weird at first, but through using Newton's second law and the energy principle, we can gain a really good understanding of how the spring moves. And with that knowledge, we can then apply it to real-life situations, such as rock climbing. So some of the formulas I used were the velocity and position update formulas, which allowed me to analyze the motion of our system. I used the energy principle, where I knew that I was analyzing a closed system, which meant W and Q would be 0, and delta E would factor into it the kinetic energy, the gravitational, and the spring potential energy. And then my period formula, I could rearrange that to find my spring constant K. So here is the tracker video that I analyzed. As you can see, we have a spring oscillating in every direction, and on the right we have just a little sample of my actual tracker data. So as you can see, here are my initial conditions. On the left I have what I did to calculate them. I rearranged the period formula to solve for K, and in order to find the period, this is the period based off the x direction, where I took an estimate and I averaged the first 4 oscillations. And then down below I found my L naught by realizing, you know what, my system's in equilibrium, static equilibrium at the very start, so I can do this little math section to find L naught. And I also knew that I was starting at rest, so my velocity would start at 0, and my initial position was given by tracker. Here's my code for the computational model that used the oscillation in the y direction. I have my initial conditions specified through here. Right here, I calculated my L vector, or the location of the spring. Here I defined what energy is, just using the formulas. Through this section, I have the while loop that not only told me the change in energies, which is down at the bottom, but also the change in position, which is up here at the top. And when I run this program, I can choose my appropriate CSV file, and this is what I wind up getting. Now keep in mind that this model uses oscillations in the y direction. Later on I'll be looking at oscillations in the x direction, and I'll be able to compare the two. Here are my energy and position graphs for my system. The energy graph behaves as normal and accurately predicts the model's energy. The position versus time graph between the model and tracker are virtually identical. The only difference is that tracker produces a graph with a smaller amplitude. This graph used oscillations from the y-axis. The first "what does it mean" question asked us to calculate the oscillation in the x direction and compare it to the oscillation in the y direction. So in the x direction, you can see that we have the oscillation is exactly the same. It's going back and forth and back and forth, and our energy graph looks near perfect, which is a little odd. And down below you'll see that the position versus time graph is definitely off. There's some weird stuff going on between here, and I believe that to be because when you look at the X oscillation, it's only taking into account the pendulum motion of the system. It's not really observing the up and down motion of the spring. Whereas when we look at the Y motion, we can see we get a lot. We have the pendulum nature going on, and we also have the spring going on. This can be seen in some fluctuations in our change in energy graph, which would be expected from our system. And also our position versus time graph matches up a lot closer. The model and the tracker data is very similar, which is a really good sign to view that the Y oscillations are probably a better representation of what we wanted. So here are the calculations I used in order to find the X and Y oscillations. As you can see, I found K, and I found L naught, and I have the period. And just at the bottom I have some notes over the X and the Y motion. More importantly is the second "what do you mean" question: is the energy principle satisfied? So I said for the most part yes. Energy is being conserved, kinetics turning into potential, and potentials turning back into kinetic, and things are looking pretty good. However, our model fails at one crucial thing. It does not account for any dissipative forces our system experiences. The model fails to recognize thermal energy, doesn't account for drag forces or anything like that. In reality, our system is eventually going to come to rest, whereas that's not accounted for in our model, so there's some discrepancy. However, for the most part, our model does a fairly good job at predicting the motion of our system.